Good afternoon. Welcome to week 11 of this course, this NPTEL course on applied optics. So, this is the second last week. Week 12 will be the last week, following which we will have one revision session as well. So, these are the last few sessions, last few classes, and I hope all of you pay attention so that you can score well in your final exam. So, this particular week, we have been introduced to special kinds of crystals which have different refractive indices for different directions, and these crystals are called birefringent crystals, which split up an incoming input ray into one ordinary ray and one extraordinary ray, both of which have different properties. For example, the ordinary ray follows the Snell's law as we have studied earlier in this course, whereas the extraordinary ray does not follow Snell's law. So, and the other topics that were introduced were special kinds of devices called the quarter wave plate and the half wave plate. So, the questions this week will focus on these topics. Let us get started with the assignment problems. The first question over here is, in a negative crystal, Ne is less than No or Ne is greater than No, Ne equals No, or none of these. So as always, I will start the poll for all of you. Please take about a minute to answer the poll, after which we will discuss the solution. Okay, so I have launched the poll. All of you please answer the poll. And if you have any question, feel free to put it up in the chat box. Also, for those of you who are joining late, let me once again put up the link to the YouTube channel for this course in the chat box. So on this YouTube channel, you would find videos for the previous sessions as well. So if by any chance you have missed one of the previous sessions, you could go ahead on that YouTube channel and watch the recordings of those sessions. And the notes, these lecture notes, are also available. Okay, someone is asking where will the lecture notes be available. So if you click on the YouTube link, there you will find videos, video recordings of these sessions, and in the description of those videos you would find another link where you will be able to find out the link for these lecture notes, the PDF form of these lecture notes. So I hope that clarifies. Okay, some people are asking about the dates of the exam and the format of the exam. For this, you should make use of the forum and contact the NPTEL authorities. I'm just one of the TAs. Maybe I'll get in touch with the other course TAs and help you out with this. But if you put it up in the course forum, there even the instructors and the other course TAs are available, and most probably they will answer your query over there. Yeah, I'm sorry, I'm not so fully aware of the final exam. So if you have seen the format of the assignment questions, the quizzes that you have every week, is that there are 10 MCQ questions and you have to answer them, and each question carries 1 mark, and all these questions that we solve in these live sessions, they are from the previous year's course. So last year also this course was running, and these are the assignment problems that were put up when when the course ran last time. So if you solve these previous year's questions, then you would be very well prepared for your assignment and for your quizzes and even for your final exam. Okay, I see some students have still not answered the poll. Please do answer the poll. Okay, so as all of you have answered the poll, let us now discuss the answer. The correct option is, wait, let me get my pen. Yeah. The correct option is option A. NE is less than NO. For this option, option B, it would be called a positive crystal. Okay, and let me write down some expressions for the velocities of the ordinary and extraordinary rays. So this is for the ordinary ray and this is for the extraordinary ray. So NE and NO are the refractive indices for the extraordinary and ordinary rays. Now over here, theta is the angle between the ray and the optic axis of the crystal. And so if you see that when theta equals to 0, then we have the velocities being the same, and this equals the following. So along the crystal's optic axis, the velocities for the ordinary and the extraordinary rays would be the same, and at in all other directions they will be different. So I hope this clarifies the question. Let me just check the chat box on this Zoom meeting once, if there are any more questions. And let me check the YouTube channel as well. Okay, so this third option that is there, Ne equals NO, that would mean that the crystal is not a birefringent crystal. It has just one refractive index all throughout. Okay, so let us now move on to the next question. Let me write down the question. So the question is on quarter wave plates. A quarter wave plate introduces, so this time I'm writing the questions also now, because sometimes the space that I anticipate is a bit less, and also to accommodate questions from all of you. Okay, so this is the question. These are the options. A quarter wave plate introduces, option A, a phase shift of pi by 4 and path difference of lambda by 2. Option B, a phase shift of pi by 2 and path difference of lambda by 4. Option C, a phase shift of pi by 4 and path difference of lambda by 4. And option D, none of these. So let me refresh the poll and restart it. Okay, someone is asking in the chat that they're not able to access the poll. Okay, so if you are on Zoom, which I believe you are, that's why you're able to log into this meeting. So in the Zoom app, I'm not sure if this is there on the Zoom browser or not, but in the Zoom app, whenever I launch a poll, you will see a notification screen and the poll will come on your screen. Unless, of course, if you close that, once you close that, I don't know from where to bring it up. But the moment I launch the poll, it will come up on your screen itself. And there will be options, and you can select one option out of these 4 options and then hit submit. And once you answer, you will not be able to re-answer. Means there is no scope of correcting your option. So if you have answered incorrectly, nothing really can be done about it. So 2 kinds of phase retarders, as they are called, we have studied. One is quarter wave plate and one is half wave plate. Next question would be on half wave plate. This question is on quarter wave plate. Please answer the poll. Okay, are you able to hear me? Someone is saying that they are not able to hear me. If that is the case, I request you to uh, like log out and log in once again, or disconnect your mic and then reconnect it. I think on YouTube I can hear the audio properly. So if Zoom is not working for you, you can try out YouTube as well. Okay, let me discuss the answer now. So the correct option is option B. Oh, let me change the color of my pen. Option B, a phase shift of pi by 2 and path difference of lambda by 4. So quarter, as the name suggests, it introduces a quarter wavelength path difference between the components. So which components? This phase shift or path difference is between the components which are parallel and perpendicular to the optic axis. And as you might recall, phase difference is equal to 2 pi by lambda times path difference. So even if you did not know what a quarter wave plate does, you could still select the correct option by eliminating the incorrect options. So you can see that if my path difference is lambda by 4, so if let's say path difference is lambda by 4, then that gives me a phase difference of pi by 2, whereas so option C cannot be correct. Lambda by 4 cannot give a phase shift of pi by 4. Similarly, if my path difference is lambda by 2, then phase shift would be pi. Again, option A is incorrect because lambda by 2 path difference cannot give me a pi by 4 phase shift. Okay, so let us move on to the next question. The next question is on half wave plate. Similar question. The purpose of a half wave plate. So a half wave plate introduces 4 options again. Sorry. I'm not keeping well today, so pardon me for that. Okay, so this is question 3. Please take about a minute or two to answer this. Okay, so let me now discuss the answer. The correct option is option A. Oh, sorry, again, wrong color pen. Option A is the correct answer. Again, you could use this expression right here between phase difference and path difference to rule out the incorrect options. Okay, let us move on to the next question. Question number 4. If the E field and D field are pointing in different directions, directions in a medium, then the medium is said to be A, isotropic, B, anisotropic, C, homogeneous, or D, all of these. Once again, I will clear the poll responses and refresh it for all of you. So, just to remind, D vector is the electric displacement vector. And E is the electric field vector. Okay, so let me discuss the answer. The correct option is option B, anisotropic. For isotropic medium, both E and D field vectors, they point in the same direction. And the relation between D and E vector is D is equal to epsilon E. And this epsilon, which is the relative permittivity, is a tensor. So what do I mean when I say it is a tensor? It means that I can write it in the following matrix form. So these are the components. Ex is electric field vector in the x direction, Ey is the electric field vector in the y direction, and Ez is the electric field vector component in the z direction. Similarly, dx is the electric displacement vectors component along the x direction, dy the component along y direction, and dz the component along z direction. And this is how they are related by this matrix for epsilon. And if we diagonalize this matrix for epsilon, if we diagonalize, then we get to a coordinate system known as the principal axis. And in that principal axis coordinate system, the matrix for the epsilon tensor is a diagonal matrix and looks like this. Now in this, if epsilon x is not equal to epsilon y, which is not equal to epsilon z, then we have what is known as a biaxial crystal. If epsilon x equals epsilon y not equal to epsilon z, then we have a uniaxial crystal. And if epsilon x equals epsilon y, which further equals epsilon z, then it is an isotropic medium. And in this medium, as mentioned over here once again, both the electric field vector and the electric displacement vector point in the same direction. Another thing about this permittivity tensor is that it is symmetric. Symmetric meaning epsilon xy equals epsilon yx, epsilon xz equals epsilon zx, and epsilon yz equals epsilon zy. So that means that, let me highlight it. So these two terms are equal. Let me change the color. How do I change it? Oh, it did not get changed or what? Yeah. These elements are equal, and another color, let's say maybe this blue, these elements are also equal. So if I were, okay, let me get it back here. Yeah, if I were to count the number of independent elements, then it would be these elements right here. So 6 independent elements in this permittivity tensor. So there are a total of 9 elements in the permittivity tensor, out of which only 6 are independent elements. The remaining 3 are same as 3 other elements because of the property of symmetry. Okay, so we can move ahead. To the 5th question. A quartz crystal with NO equals 1.54425 and NE equals 1.55336 for wavelength lambda naught equals 5000 angstroms. If this crystal introduces a phase shift of theta equals pi, then the thickness of the crystal will be A 27.4 micrometers, B 27.4 nanometers, C 27.4 millimeters, or D 0.274 millimeters. So again, just to remind, NO and NE are the refractive indices for the ordinary and the extraordinary ray respectively. So that means this is a birefringent crystal. It has different refractive indices for the ordinary and extraordinary ray. Quartz is a birefringent crystal. Quartz and calcite, these are two popular and commonly used birefringent crystals. Oh, sorry, I forgot to refresh the poll. Let me refresh and relaunch the poll. I see some students are not answering the poll. All of you, please do attempt the poll. Sorry. Okay, so let me discuss the answer. So we have the expression for thickness in terms of the refractive indices and the phase shift that is being created. So theta is the phase shift. Theta is the phase shift. NO and NE are the refractive indices, and D is the thickness of the crystal. So thickness of crystal is D. So we can convert this c by omega into lambda. So this is lambda naught over 2 pi no minus ne theta. And how we got this? That's because omega equals ck and k is 2 pi by lambda. So from here you get c by omega is lambda by 2 pi. Now we can plug in the values. So for us theta is equal to pi, so lambda naught pi over the following, then pi gets cancelled out. This gives us lambda naught over 2 no minus ne. Now just plug in the values. So lambda naught is 5000 angstroms over and we will take the mod value of this, and this comes out to be roughly the following. Which is nothing but 27.4 micrometers. So the correct option is option A. So notice that any thickness will not work. This is the particular thickness that is required for it to create a phase shift of pi. And as we have seen earlier, a phase shift of pi means that it is a half wave plate. So theta equals pi means that we want a half wave plate. For a quarter wave plate, if you wanted a quarter wave plate, then theta would be equal to pi by 2, and in that case the thickness would be lambda naught over 4 no minus ne. Okay, so if we change the thickness, then we change the phase retardance. And if you want to use the same crystal as a same crystal with the same no and ne values as a quarter wave plate and a half wave plate, then we have to change the thickness, and we have to manufacture the crystals with these precise thickness or these precise thickness values. Okay, so moving further. So if we are halfway through, 5 questions done, 5 more questions. Question 6. For the calcite crystal, another material which is used to study birefringence. For the calcite crystal, NO equals 1.68134 and Ne equals 1.4694 at wavelength lambda equals 4046 angstroms. If we consider wave vector k is making angle of 30 degrees with the optic axis, then the angle between S and K will be A 8 degrees, B 2 degrees, C 6 degrees, or D 4 degrees. So once again I will relaunch the poll. Please solve this numerical. Okay, someone is asking in the previous question, what if theta equals 2 pi? Let me answer that question. So theta equals 2 pi, that would means D equals lambda naught over NO minus NE, and 2 pi is essentially same thing as if you do modulus of 2 pi, same thing as 0. That means there is no phase shift. No, this is essentially equivalent to no phase shift if you do modulus 2 pi. Okay, so now coming back to this question. Okay, so let us discuss the answer now. Just to remind, S is pointing vector. Okay, and K is the usual wave vector. And pointing vector is given as E cross H. Now, let me draw a diagram for all of you that would help in understanding. So let me first draw the axes. This is the x-axis. This is the y-axis. Sorry, let me call this x. Let me call this z. And now z is my direction of optic axis. And let me draw k vector. So this is my k vector, and d vector is perpendicular to k vector. That's my d vector. This angle is 90 degrees. Then my h vector is coming out in the y direction. Okay, let me move this slightly up. So this is h vector, and now s and e vectors. So this is s vector and e vector is perpendicular to it, and this angle is 90 degrees. So you see E cross H, if you do this blue vector E cross purple H which comes out of the screen, then that gives you this blue vector S, which is the pointing vector. Now let me write down some angles over here. Let this angle be psi, let this be phi, and let this be theta. And this is for the extraordinary ray. Extraordinary ray. And we are given that the wave vector k makes angle 30 degrees with the optic axis. So this is our psi angle. So psi we are given is 30 degrees. And if you recollect from your lecture notes, then the expression for phi in terms of psi is as follows. Now I need to pull out my calculator to find out this. All I need to do is plug in the values. I have NO, I have NE, and I know my psi, which is 30 degrees. I just need to plug in the values in this expression to get phi. Phi is the angle between S and K, that is the pointing vector and the wave vector. Okay, so let me put it in the calculator. NO squared, that means 1.68134 squared, divided by NE squared, so 1.49694 squared, and tan of 30 degrees. Tan of 30 degrees is 1 over root 3. So tan inverse of this, so what does this come out? Tan inverse of this comes out to be roughly 36 degrees. Minus psi, which is 30 degrees, gives me 6 degrees. So the correct option is option C, 6 degrees. So you have to be one thing to note over here, you have to be careful whether you are taking your angles in radians or in degrees. Don't mix up the two. So if you are working in degrees, then you should work in degrees throughout. If you are working in radians, you should work in radians throughout. If you put some place degrees, some place radians, then you will just mess up big time. Okay, so we can proceed further. Question number 7. Which one is true for the case of ordinary wave in uniaxial crystal? And the options are A, angle between K and S would be 0. Option B, K and S makes the same angle from the optic axis. Option C, E and D are in same direction D, all of these. So I have relaunched the poll for all of you, and all of you students, please attempt this question. Please do answer the poll. So the previous question, that was for extraordinary ray. This one is for ordinary ray. Again, K is wave vector and S is Poynting vector. Oh, someone is asking expression for Poynting vector. It is given over here. Poynting vector is E cross H. For a non-magnetic medium, H is B over mu naught being permeability of free space. Okay, let me discuss the answer. Let me once again draw this diagram. So here are my axes. Z, X, this is optic axis. I'm just redrawing the figure from the above question. That's my K vector. That's my D vector. That would be S vector. That would be E vector, making 90 degrees. And these angles, psi, phi and theta. So for ordinary waves, this one is for extraordinary. For ordinary, what we have is phi equals 0. So that means the S vector is actually coinciding in direction with the K vector, and that means that the E vector coincides in direction with the D vector. So that means angle between K and S is 0. That's true. K and S make the same angle from the optic axis. That is also true. And E and D are in the same direction. That is also true. So all these options are true. All of these. Okay, moving ahead. Question 8. A Polaroid is introduced in the path of the beam and Polaroid is rotated about the direction of propagation. Sorry, of the beam. If there is no variation in intensity, then the correct statement will be A. Light beam is circularly polarized. B. Light beam is unpolarized. C. Light beam is a mixture of unpolarized and circularly polarized or D, all of these? So this question is on trying to characterize the polarization of an incoming beam by using polarizers and combinations of wave plates. So here we are using one polarizer or Polaroid, and we are rotating the Polaroid, and we see that there is no variation in intensity in the output for the given incoming beam, and we need to figure out what kind of polarization is for the incoming beam based on this observation. Okay, so let us discuss the answer now. Let me first draw the polarizers. Let me draw a diagram for all of you. I'll copy this. Okay, so what we have is a polarizer, then a quarter wave plate, and then a polarizer. This is the setup that I am creating. What we are told in this question is what we see after this first polarizer, and to analyze we will keep an additional construction by keeping a quarter wave plate followed by a polarizer again. So let's say this is the fast axis of the polarizer. Okay, I'm not able to draw it right through the middle. Okay, I need to zoom in. Okay, so this line denotes the fast axis. We will keep the quarter wave plate fixed and rotate the polarizer. So what happens if we send in circularly polarized light? So if we send in circular through the linear polarizer, then the output is also a circularly polarized light. And because it is circularly polarized light, if I rotate my polarizer, I will not see any change in intensity. So as a result, I'll just see I naught by 2 if my input intensity is I naught. If here it is I naught, then I will see I naught by 2. And if I rotate my polarizer, I will see no variation. After the quarter wave plate, this will become linearly polarized. And after this polarizer, what I will observe is, let me draw the axis. I'm going to observe something. Okay, this is not looking nice. Let me draw it a little bit better. Okay, this is my best attempt, I believe. This is theta, this is I. This point is I naught, or let's say 1. We will normalize this by I naught, and this is 0. And this comes from Malus law. Malus law, which says that output after a polarizer is I naught cos squared theta, where theta is angle between a polarizer pass axis and linear polarized or direction. Okay, now if I send in unpolarized light, then what happens if I send in unpolarized? Sorry, this remains. Let's not. Yeah, sorry, this is I, this is I naught, and I naught by 2. And after this, whatever is the final intensity, we will normalize it to that. So if I send in unpolarized light, then after the polarizer also it is unpolarized. So if it is I naught here, it is I naught by 2 here, and again we will not see any variation in intensity. So after the quarter wave plate, again it is unpolarized only, and after the polarizer, so if it is I1 here, then it becomes I1 by 2. finally, if we send in a mixture, the third option is mixture, a mixture of unpolarized and circularly polarized light. If we send in a mixture, then we get a mixture here. So again, no variation in intensity. Then we get a mixture out of the quarter wave plate as well, and final result is, let me draw the axis. I theta, again normalized intensity, and what we will see is, we will see like this. It does not go to 0, so maximum is 1, like this. And if we see this from here, this peak to this peak, this is 2 pi, and this peak to this peak here also it is 2 pi. So this does not go down fully to 0. That's because it is a mixture of unpolarized and circularly polarized. If it is purely circularly polarized, it goes all the way down to 0. If there is some component of unpolarized light beam as well, then it does not go down fully to 0. Okay, good. So we can proceed further. Question 9. Question 9 is also based on question 8 as well. So up until this point, does anyone have any question? Let me just check the YouTube channel as well as the Zoom chat. Okay, someone is asking, why is this 2 pi? Why isn't, okay, what happened? Yeah, why isn't the distance between these 2 points 2 pi? Because between two successive maxima, we typically call it 2 pi, but here I'm saying it this way. This is because of cos squared theta. This is not just cos theta, it is cos squared theta. So if I were to draw cos theta and cos squared theta on the same graph, oh sorry about that. So if this is my axis, okay, today I'm not able to draw straight lines. Okay, here. So if this is my axis, and cos theta would be like this, one period, and then successively starts the next period. Whereas cos squared theta would be something like this. So because it is cos squared theta, it will never go negative. You see, now this is theta, this is cos theta, this is cos squared theta, and you see that my 2 pi is over. If this is 0, this is 2 pi. And you see, for cos theta, in 0 to 2 pi you have one peak, whereas for cos squared theta, between 0 to 2 pi you have two peaks. So that's why. I hope that clarifies the question. Okay, so now we can move ahead. So question 9. A Polaroid. This question is similar to the previous question. A Polaroid is introduced in the path of the beam and Polaroid is rotated about the direction of propagation of the beam if there is a variation, this time there is a variation, if there is a variation in intensity without complete extinction, then the correct statement will be A. Light beam is elliptically polarized, B. Light beam is mixture of linearly polarized and unpolarized light. Option C. Light beam is mixture of elliptically polarized and unpolarized light. Option D. All of these. So this, if you see, is similar to the above. In question number 8, there was no variation in intensity after the first Polaroid. In question number 9, for this particular question, there is a variation in intensity after the first Polaroid, but this variation is such that there is no complete extinction. No complete extinction meaning it does not go all the way down to 0. Okay, so the poll has been relaunched. Please attempt the question. Okay, let us now discuss the answer. Once again, I will draw the same setup. So we have the polarizer, then the quarter wave plate, and then another polarizer. Okay, this looks different. Let me copy paste. Okay, let me draw the pass axis. So polarizer, quarter wave plate, and polarizer, and we rotate this, keeping the quarter wave plate fixed. And once again, the question is measuring the intensity after the first polarizer. So let us say the input is circularly polarized. So circular, after the first polarizer it remains circular, and just like previously, if this is I naught, this will be I naught by 2 and no variation. And after the quarter wave plate, this will become linear, and linear when it falls on the polarizer, it will follow Malus law. So okay, why is it not working? These are my axes: theta, normalized intensity, and okay, this does not look that good. Today I am not able to draw things properly. I don't know why. Okay, that's my best attempt. 0. And once again, this is coming from Malus law, which says that the output intensity is I naught cosine squared theta, where theta, let me just copy it from here, theta is the following. Theta is the angle between polarizer's pass axis and linear polarized direction. Okay, so this is for, oh sorry, why am I doing circular? Okay, I'm sorry, this was supposed to be for elliptical, but the result is the same. Meaning if I send an elliptical after the polarizer, it is elliptical. Okay, in the previous question, what we had seen was that at the output there was no variation after the first polarizer, so constant intensity like a flat line. And here what we are seeing is that there is variation in intensity, but it doesn't go all the way down to 0. So this is my 0, and there is not a full extinction. Okay, so elliptical remains elliptical after a polarizer, becomes linear after quarter wave plate, and then we see Malus law after the second polarizer. And if we send in a mixture, so we send in mixture, then it remains a mixture after the first polarizer, and it remains a mixture after the quarter wave plate. And there are two kinds of mixtures over here: linearly polarized with unpolarized, or elliptically polarized with unpolarized. And the difference in the two would be as shown over here. Let me draw the axis once again. So this is theta, this is the normalized intensity. So this is 1, this is 0. And the difference is, so let's say for here, this was 2 pi, let me just remind. And here again, this will be 2 pi. And the difference between these two mixtures can be found as follows. So let me draw one more cycle. So this is another 2 pi. And if I look at this point where we have the peak, and if this angle or any of these peak angles is, if the angle is same as the angle after first polarizer, then we have mixture of unpolarized plus linearly polarized. Whereas if this angle is different from angle after first polarizer, then we have a mixture of unpolarized light with elliptical. So this is how you would measure, this is how you would distinguish between these two mixtures, by measuring this angle. Okay, great. So now we move on to our last question for the day. Let me go to a new page. I don't have much space over here. So the last question for the day. A circularly polarized light passes through a quarter wave plate. The state of polarization of light after the quarter wave plate would be A, same, B, elliptically polarized, C, linearly polarized, or D, unpolarized. So I will relaunch the poll for one last time for today. Okay, so let us discuss the answer. The correct answer is linearly polarized. So when circularly polarized light enters quarter wave plate, it becomes linearly polarized. We saw this in this question as well. We saw that circularly polarized light entered over here. Circularly polarized light entered a quarter wave plate and it became linearly polarized after the quarter wave plate. This we can also see from what is known as the Jones calculus. So Jones calculus is a way in which you treat polarization in the form of matrices. So for quarter wave plate, having the fast axis at angle theta with horizontal, the Jones matrix is as follows: e to the power minus I pi by 4, then cos squared theta plus I sine squared theta, 1 minus I sine theta cos theta, so this is the Jones matrix for the quarter wave plate. And for left or right circular polarized light, we have the Jones vector, which is given as follows. So plus is for left circular, minus is for right circular. For horizontal, the Jones vector is this. For vertical, the Jones vector is 0, 1. So now the output after the quarter wave plate, output of circularly polarized light as input, is you have to take the quarter wave plate matrix and multiply it with either left circular or right circular polarized vector. So this gives me e to the power minus I pi by 4. This is for quarter wave plate. Times the vector for left circular. Okay, so keeping these constants out, these are just constants. And we need to do now this multiplication. So cos square theta plus I square theta times 1 plus I times 1 minus I sin theta cos theta plus I times and then I squared is minus 1, so minus cos square theta. Now I can do some simplifications. Okay, I can do like this: cos squared theta plus I sin theta cos theta oh sorry, not I. So let me separate the real part and the imaginary part. So I squared is minus 1, so this gives me sin theta cos theta. Now I can take some things common. Oh sorry, cos theta common from the first term. I sin theta common in the second term. Now I can take more things common. Yeah, I can take more things common, right? So I can take cos theta plus sin theta common in the first term. This leaves me cos theta plus I sin theta. Then in the second term I'll take sin theta minus cos theta common. This leaves me once again with cos theta plus I sin theta. And so cos theta plus I sin theta is common to both. So it comes out. It becomes another constant. And cos theta plus I sin theta is nothing but e to the power I theta. And this is just some constant a, and this output is linear polarized. Why? Because you see that this is nothing but a times sin theta plus cos theta h plus a times sin theta minus cos theta v. And there is no phase difference between h and v. They are in phase. There is no additional imaginary term, I kind of term, So there is no phase difference between H and V. They are in phase. So that's why this is linearly polarized. And the angle can be found out as follows. So whatever is the angle theta, you can find out this angle. This is the angle of the linearly polarized light. So if this angle is alpha, then your linearly polarized light is like this, making angle alpha. Okay, so this brings us to the end of this week. Thank you so much. See you in the next week, which would be the last week. And of course, there will be a revision session. Bye bye. Yeah, thanks everyone for coming up.